doing some experiments, making some calculations, predictions, and we're gonna see what all these devices do. What is that? Cans. Oh my god. Tuning fork.
Tuning forks are useful in music because they have a very well-defined oscillation frequency. And so two identical tuning forks, so they produce exactly the same sound, but by making the mass a little larger on one side, I can change the frequency a little bit. Can you hear the difference in sound? What do you hear?
That's a half note.
Yeah, you can hear the beats because they're off.
Beats, you can hear
Oh, beats.
So those are beats. Remember we talked about beats?
Yeah, it's off by some frequencies.
Quick question. So if the frequency of this is omega 1 and the frequency of that is omega 2, what is the beat frequency?
There's a delta omega.
Delta omega. The difference of the two frequencies, right?
Yeah. We can hear a little resonator. It's trying to like measure the frequency. It's like buzzing and stuff. Now it's vibrating. So we have the oscillator. We're getting a single standing wave here. I think we're trying to get two standing waves going. You kind of see it.
Can you see that from there? Yeah.
There's two waves there.
What is the next frequency? The first one was 16 and a half.
33.
This is 33 hertz.
Yeah, is it 2F1?
What do you think they stand for? Waves?
Oh yeah, these are waves.
On the water?
Circular orbital waves.
So I have two of them. I'm going to put them on top of each other. And imagine that I'm now looking at two waves superimposed.
Yeah, superimposed waves. Interference.
A little reminder of that. You calculate interference patterns. Let's do this.
Yeah, they're like moving.
So, notice when they're very close
Oh, they're spreading.
Spread with the middle.
Whoa.
Exercise in class. I ask you to try this.
We might have to move around.
Left and right.
Yeah, it's getting a little louder here. Definitely much louder.
Oh, that's crazy. You can, yeah.
You can
Yeah.
hear it?
It's almost like beats.
And then,
It's like, wow.
As we come to this side, it's getting quieter now. You can't really hear it
Yeah,
right
you can hear
here.
it. That's crazy.
Yeah, so it's like we're imitating
Let's
the
go to the back. You can probably feel it more.
patterns on the wall. Where can we not hear this at all? This is weird.
So this is no weight, and then there's a weight. I can put in equilibrium. It got extended by that much.
Mg divided by K.
Mg divided by K. And then if I say, what is the frequency of oscillation?
Square root of K over M.
There we go.
Square root of K over M. Yeah.
Two different strings with different K values.
Well,
We'll see. Oh yeah.
right.
Slightly.
So they have different K values. Which one has larger K value?
The
The one on the right?
So which one is going to oscillate with higher frequency?
The one on the right.
Oh, because
Because
the tension's
Yeah.
higher.
Well,
Or-
and also because the frequency is square root of K over M.
square root of K over M.
Big one.
Oh.
Go to the other direction.
Hopefully it doesn't break.
So this is a factor of 2, so it's root 2 difference in frequency.
Oh, and it doesn't matter the amplitude.
The normal mode of oscillation here is a complicated combination of both.
So
And if
this
you don't have them,
spinning-
then you can go from one to the other.
Oh, I like how like the side
Can
and
you
then
guys see that
it,
in the back?
cycles in and out of like phase.
Yeah.
It does.
So then the
Yeah, the
two
spinning
like,
stopped.
The two extreme modes
And
would
then
be
the spinning starts again.
Only
Yeah,
the
yeah,
bottom
like now it's
part
in-
rotating, and then the other extreme mode would be just.
Those are not the normal modes. Those are the extremes, but
Side
those are
and
not
then
Yeah.
the normal.
So like
Right?
right now it's more in
The
phase,
normal
but
modes
then
are combinations.
it's like getting less out of phase now.
Now it's out of phase? Yeah, it's out of phase
Okay,
because
so
it can't move.
that's a couple of oscillators very
Oh my
I
god.
think they're also
It's not too hard to actually
so it's like
work out.
It's interesting.
it looks like magic at first, right? Because you put it in here and the other ones go up. And they go up to exactly the same height. But that's because there's a connection at the bottom. There's a pipe that connects them all. So what is that?
Bernoulli's principle or something?
Pressure balance between all of them.
Yeah, I think it's Pascal's.
Pascal's principle.
Pascal.
Yeah.
Nice.
That
It's the
whatever
same.
equation
So what is the pressure at the surface of this one?
road gauge.
One atmosphere.
Oh, yeah.
And that one?
Atmosphere.
And one atmosphere. And you can see the pressure is the same as a function of height,
Yeah.
regardless of where you are.
It's so cool.
Interesting.
So
Thing from like
Okay.
badminton
I'll
or
explain
something.
what it is after I do the demo, but maybe you guys can try to figure it out. So I'm gonna press this really hard.
Oh no.
Oh,
Oh. Okay. So.
Huh.
Hmm?
wait, is it the squid is like I'm assuming there's an air pocket inside of it?
Uh-huh.
Okay.
It's submerged, so the fraction of the submergent thing, the density of the object suddenly became really heavy
yeah,
or something.
Exactly. Yeah, there's more water, so the like.
Air's compressible and water's not.
No, I guess before it is right. There's less.
Very interesting. Air is compressible,
In the
water
high.
is not. So how do I Okay.
Oh,
so
I
learn
can-
some things. You said
You
the
increase
squid
the
has air
density,
in it,
yeah.
right? And the squid actually does have air. Now there you said air is compressible and water is not. So what did I do by pushing here?
Increase the pressure.
Increase the pressure. So the pressure gets high, but the density of water doesn't change.
So the objects
The thing would actually
shrunk?
sink if what?
The density of the object is greater than water, and it becomes greater.
Right, it
because-
becomes greater than
Squish
water.
the
It has
air out.
air in it, but when you
It
compress
has air in it, and somehow when I press, that air has to be compressed.
Oh my god.
This is a vacuum pump. I'm gonna connect the vacuum pump to
Making a vacuum sealed set
and
of cylinders or spheres.
Oh wow.
It's vacuum sealed.
Well, what's happening?
It's gonna be hard to pull it apart.
what? Spoiling. Okay. But if the pressure is lower on one side than the other, what do you expect would happen on this side versus that? Even though they have the same.
Rice on the left side.
Right. So let's see. So this side is higher than that, which would not happen if we had an actual flow with the same pressure. But because the pressure is lower here, you can see that, right?
And the
Pressure is higher than that. But still, the one in the middle
down with the height.
is much higher because
The velocity is the greatest there, so most of the energy is kinetic instead of potential.
right. So you see that, right? The velocity is much higher in the middle. So we got it down to what? You want to have like 4 psi? So let me heat it up a little bit. This is the part I want to have some distance from it.
The pressure's going up.
Oh, it's like,
Yeah. Pressure's really high now.
4 to 16, 4 times the pressure, the volume didn't change and didn't change. So the temperature,
There was heat transfer.
yeah, what is the temperature that I reached for the gas?
4 times 273.
73.
Yeah,
It's like 1,000 then.
yeah, it's over 1,000 degrees
Jeez.
Kelvin. So I have 1,000 degree Kelvin
That's pretty cool.
and it's cooling off, and I can cool it off faster, which is kind of fun.
oh god.
I don't know how long I have to do this for so try that.
Oh, it doesn't fit through the hole anymore.
Wow.
I'm really pushing that way.
Oh my gosh, there we go. That's intense.
We just make some more fun.
Is it made of two metals?
It's Bilbo's dagger.
No, it does that because I think it's slightly leaning, right? So when you like heat it up, the material becomes more pliable.
Or is it made of two sheets?
It's made of 2 sheets of different metals. So there's a metal. They have different expansion coefficients.
No way.
Oh.
Back to being straight. Incredible.
Where's the
Oh, it's spinning now all of a sudden.
Oh, and then it spins.
Dang, look at that.
Oh my god. Wow.
Angular momentum.
And then it spins because it's an object. Yeah, you're right.
It's like a little train engine.
Oh, and that's the work. Yeah, oh, it's literally just an engine. Oh, it's literally just an engine.
But you can do like assuming that you keep it at a constant temperature. It's basically
It's slowing down because it's cooling off.
yeah.
To save the day with the prongs. Yes.
Let's do it.
Thank you.
We didn't get tongs.
This is the last time we get to see all the experiments lined up like that. Pretty amazing. And we're getting prepared for this interesting one.
So remember what we expect. Nothing to happen.
Oh.
Absolutely no.
Oh my god.
That was way faster than I.
That was crazy.
Just shriveled up.
That was insane.
Goodbye.
Let's try another one.
Here we go.
Here we go.
Oh my god.
Ready? Go.
Yay!